Hello and welcome everybody to this talk about machine learning lifecycle made easy. So we've got two talkers here today. We've got Kalyan and we have Karishma. Um, so Kalyan is a machine learning specialist at S&P Global Market Intelligence and has 5 years of experience working with the intersection of data science and automation in various domains. Karishma is also currently working as a machine learning specialist at S&P Global Market Intelligence from India. They are both working with they're both working with MLflow, and they're here to tell you a little bit about how to apply it in your lives. So take it away, you two.
Perfect. Thank you, Sheena, for the lovely welcome. And here we go. Good afternoon, everybody. Thank you for joining in. This is our first time speaking at PyCon South Africa. And Kalyan and I are really excited to spend the next 30 minutes or so with you all talking about the life cycle of machine learning projects, challenges involved, and how MLflow can be leveraged to address those challenges. So, without further ado, let's get started. Here is an outline of the session. We'll begin by discussing the typical life cycle of a machine learning project, followed by the development challenges encountered at each stage of the project. We will then introduce MLflow, its components, and how each of those components address the development challenges that we earlier talked about. And with the help of an example, we would like to demonstrate each element of MLflow and also give you an overview of how you can get started, and we would be taking any questions you may have at the end of the session. So, let's get started now. So, creating machine learning solutions to various problems can be quite the arduous task. Until recently, we all have been learning about software development life cycle and how it goes about requirement gathering, designing a workflow, development, testing, deployment, and all the way down to maintenance, right? And we are also studying the various models that we can use for software development, such as waterflow model, iterative model, and agile models, right? But now we are at a stage where we want to leverage the incoming data more by means of machine learning. This new requirement transforms the traditional software development lifecycle to give way for a machine learning life cycle. And beyond the usual conventions and concerns in software development, machine learning development comes with its own additional challenges. The usual process for building an end to end machine learning project involves collecting and processing raw data, analyzing it, applying featureization steps, training different algorithms, evaluating them, and deploying the best model on a platform that enables user access. It seems fairly straightforward, right? But in reality, it is not. There are several complexities that arise along the way due to the circular nature of this process. So, everyone who has tried out machine learning in some form or the other knows that there are multiple tools, modules, frameworks out there at our disposal for each stage of this life cycle, whether it's for preparing data, training models, or deploying them in production. For instance, data can be stored from multiple storage units, including but not limited to Amazon S3 buckets, Azure Blob Storage, DynamoDB, traditional SQL databases, and so on. This raw data would then be analyzed, cleaned, processed using Python libraries or R libraries such as sklearn, pandas, and NumPy. Depending upon the problem that we are solving, we may build countless regression or classification models for textual, visual, or tabular data. And finally, deploy these models either in Docker containers or host them as a Flask web application. As much as it is a boon for us developers to experiment with multiple state of the art ML libraries and frameworks to get optimum performance, it is also a pain as it poses various difficulties in tracking these experiments, reproducing the same results from the same code, and productionizing dozens of libraries. For instance, when we want to experiment with several algorithms, right? Our go-to strategy for tracking the parameters results and evaluation metrics for each of these algorithms looks something like this, right? And we create several notebooks, and each of them have the word final in it, right? Otherwise, it's not worth looking at the notebook either. So, the continuous nature of ML development lifecycle requires constant tracking mechanisms to facilitate comparison and reproduction of results, right? However, ML is not just code. ML is code plus data that we need to keep a track of. But that's not where the story ends. If you thought building machine learning models was hard, putting them into production is even harder, right? We often have to rewrite our code before moving a model from development to staging to production, and this is a really time consuming task, and it also poses a lot of risks, such as we can introduce new bugs while we are rewriting the code that can eventually lead to data drift, concept drift, and infrastructure changes, right? That eventually lead to model degradation over time. But this is absolutely normal. In some cases, we might want to retrain the model completely. That takes a lot of time and effort, or build a new model altogether to cater to the evolving data, and the unending cycle again begins. We take the raw data, analyze it, train a model, and then deploy it. In a nutshell, if anything changes, everything else also changes. Not to forget the three pillars on which model maintenance in production depends: scale, monitor, and governance. While code is carefully drafted in a controlled development environment, data comes from the unending entropy source that is known as the real world. Also, it is crucial to scale the model to handle large volumes of incoming data, monitor model behavior to detect bias and degradation, and account for drift. Model governance is also another task which is extremely important. Starting from experimentation to deployment, we want to track everything from auditing purposes. And referencing back to the keynote we had yesterday, given by Jade, where she mentioned model governance can be thought of as cataloging every step of this process. Think of a nice librarian who is kind enough to catalog everything. So it is very important in order to reproduce the same results, test if the model has degraded in production, what is the accuracy, and in order to avoid any inaccuracy. So this eventually sums up ML Ops for us. MLOps is relatively a new and exciting discipline that operationalizes machine learning models from experimentation to production with tools and frameworks that are very rapidly evolving. If this did not convince you that MLOps is important, I think maybe Elon Musk can convince you for that. Now, enough about the challenges. Let's dive deep into standardizing the machine learning lifecycle with an open source solution developed by Databricks. MLflow was developed by Databricks and released as an alpha version in June 2018. It is inspired by the existing customized ML platforms that have been developed by various tech giants such as Facebook, Google, Uber, but it has a key distinction with that. This module, MLflow, is open source, whereas the former are completely limited to their parent organizations. MLflow is compatible with numerous libraries, algorithms, development tools, and frameworks of Python as well as R. Its modular and API first approach allows you to integrate it easily with your existing ML code base without making any significant code changes. And it is designed in a manner that is platform as well as tool agnostic, thereby, it allows maximum flexibility. Today, MLflow is compatible with various frameworks such as TensorFlow, PyTorch, Keras, Apache Spark, Scikit-learn, Docker, Kubernetes, Amazon SageMaker, Azure Machine Learning, and so on. MLflow framework is being utilized and contributed to by organizations such as Microsoft, RStudio, Facebook, Booking.com, and many other from the open source community as well. So I would encourage all of you to read about these contributors and their work on the official mlflow.org website. Now coming to the components, there are three key components of MLflow open source version. And these include MLflow Tracking, MLflow Models, and MLflow Projects. MLflow Tracking provides you with an API and a user interface capability to ease bookkeeping and visualization of your experiment results, as well as runs across different frameworks. The second component is MLflow Models, which facilitates model serving onto a development deployment tool of your choice. And last but not the least, MLflow projects. It allows that a model be packaged in a manner that allows for maximum reproducibility, whether it's across local platforms or cloud platforms. So let's circle back to each of these components and see how they address the development life cycles of a machine learning project. So let's start with the raw data. Data for a machine learning project, as we can think, can be in any form: text files, CSV files, and these can be processed either in batches or in the form of streaming data. MLflow Tracking API allows the user to log all the data files that they are using to train or test a model. Additionally, Tracking API also helps you record the steps involved in data preprocessing, such as cleaning, missing data imputation, followed by featured selection and engineering, and lastly, transforming the data to make it ready for your models. Lastly, MLflow Tracking does what it promises. It helps you track various experiments with numerous algorithms, hyperparameter tuning, model comparison, and evaluation metrics. One component, that is MLflow Tracking, and it takes care of 3 stages of your machine learning lifecycle. That's pretty neat, right? Now, once we have retrieved our data, processed it, and fed into a model, we are ready to serve it onto production. And this is where the trick lies, and integrating a model into a deployment tool. And the primary avenue where machine learning models fail mostly and do not make it into production for final use by the users. MLflow models component comes to rescue here. It helps you package models into different formats, also known as flavors. And a flavor can be a Python function or an sklearn function or a Spark function, and so on. These flavors that the model is available in would again be listed in a very descriptive manner in a file known as mlmodel.yaml file. It helps you run through all the flavors a given model is available in and how you can reproduce it and deploy it on different tools. For instance, suppose we have a model with suppose a Python function, and it's of the Python flavor and can be deployed on a Docker-based REST server to cloud platforms such as Azure ML or Amazon SageMaker, or as a user-defined function in Apache Spark for batch and stream processing. In the end, MLflow Projects ties everything together very neatly by facilitating the reproducibility and reusability of the packaged model for local and cloud execution. Now let's dive deep into MLflow tracking. Here are some key concepts we want to introduce before moving forward. We have been referring to developing ML models as experiments, and an experiment can be broken down further into multiple runs, where each run signifies a piece of code that you're running, which can be logged into local files, databases, or remote servers. Code versioning is really important to maintain throughout the ML lifecycle, and the tracking API provides you with that facility as well. This is very important again to overcome the file naming problem we always have, which is final, 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 and sometimes in my case, finally, final, and so on. The tracking API also helps you log the obvious parameters such as project name or source, input parameters that the model accepts, record the evaluation metrics such as R-score, precision recall, RMSE values, and so on. Furthermore, this API helps you track artifacts. Now, these artifacts are any files can be of any format. These could be plots from your exploratory data analysis, could be your ROCA UC curve, could be your sklearn pickled models, and your data files. Now, here we depict the tracking API in a very simple schematic, which shows that the tracking API accepts any notebook, .python scripts, GitHub repos that we can run, and all those parameters associated with them, such as metrics, artifacts, would be recorded by the API and can be visualized in the user interface. We have a little code here that shows you how tracking API can be used with your usual MLflow code, with your ML model. In the beginning, we start the MLflow run. We have imported MLflow library and we are starting the run. We have logged the hyperparameter alpha here with the help of the log param functionality of MLflow. In the middle, we have the model training. It's as how we do it as usual, nothing changes there. In the end, we want to evaluate and log the model again through MLflow. And lastly, we'll log the model as well to ensure that we can reproduce the same results at a later point in time. This is now a snippet of the tracking user interface that will be covered in a lot more detail during the demo. Next, we have the second component of MLflow, and that is called MLflow models. Till now, we have created the model we want, we have evaluated it, we have decided how we want to proceed, right? Now, the need for MLflow is to streamline the process of deployment of the MLflow model on various diverse tools, such as an inference code on Docker, or as batch and streaming workflows with Spark, and existing MLflow serving tools such as AWS SageMaker and Azure ML. And you can imagine n different permutations and combinations between the MLflow development frameworks that one developer might be using and the available deployment tools. And it is not very sustainable to maintain, right? So MLflow Models API provides you with a very generic framework to serve models in different formats or flavors compatible to your deployment tools. The model file is it's a YAML file, it's a descriptor file that highlights all the flavors the model is available in. So here are some concepts that this component uses, and we have already covered flavors, that these are formats or modules that are interpreted by the deployment tools, which makes it easier for them to understand the model without the need of having a separate integration mechanism. A model signature is representative of the model schema, such as input and output parameters. Additionally, we have input example, which, as the name suggests, is an example instance the model expects. And finally, all of this is combined neatly into an ML model file. It's in YAML format, which outlines the flavors the model is available in, the model signature, and input example. This is a diagrammatic representation of the MLflow models and its functionality that is, again, platform agnostic. The snippet here shows how to deploy an ML model onto a REST API through terminal. The first command establishes the REST API server, and through the second command, that is the curl command, we are sending some parameters, input data, on which I would like the model to make some predictions. Here is the ML model file for the example that we'll be covering in the demo. The last component of MLflow is ML Projects that packages models in a standard format for reproducibility and reusability. If you have collaborated with other developers on an ML project, you can realize how difficult it is to reproduce the same code from another developer, or even from a model that you may have developed, let's say 3 weeks prior to when you're running it, right? So here, like MLflow models, ML Projects also uses a descriptor file to outline the code environment in which the model was created. It can be Docker, Conda, or local. The model entry point, or the main function with the parameters to execute the model, and of course, not to forget the project name. This descriptor file is again in YAML format. Now, next we have a very simple representation of MLflow projects again that shows how we can use MLflow project YAML file to reproduce runs on local or cloud platforms. This is how a sample ML project file looks like for your reference. It outlines the Conda environment, the entry points, the parameters, and the data type of the parameter, along with the command how you can run this code. Now, getting started with MLflow is pretty straightforward. As mentioned here, we just need to do pip install MLflow. To help you get started with some examples, you can clone the Git repo of MLflow and go through the examples in detail. We would also encourage you to read through the documentation if you would like to dig deeper into how each of these components work, how you can use MLflow with various types of modules such as TensorFlow, Fast AI, how would a deployment work for Docker, how would it differ for AWS SageMaker, and so on. Now it's time for some action, a demo. So let's get started with the demo.
Cool. I hope you can see my Jupyter notebook. Karishma, can you please confirm?
Yeah, it's visible. Can you just increase the size?
Sure.
Perfect. Thank you.
Awesome. So now that we've learned about the individual components of MLflow, we just wanted to give you a short demo of how each of these work. So here, it's all a basic import statement that we're trying to import few modules from scikit-learn and at the MLflow package itself. And we are also using an inbuilt example from the scikit-learn package on the diabetes data set. So we're trying to quantify a measure of how likely a person is going to have a diabetes there. So sort of a regression problem here. So we're generating all the dependent and independent variables here with X and Y. And we are also doing the train test split with a 25% split of 25% of the samples being in the test set. Then we're also defining our evaluation metrics here. So we're trying to capture the RMSE and R squared value to evaluate the performance of the model that we're trying to build. Right, so here comes the main part of doing our experiments. So we start with creating an empty folder if it doesn't exist, and we're trying to put in, and we call it images. And the idea is to put there some images that we generate through our EDCA process. Right, so like we discussed, we use the start run method in the MLflow package to define any of the experiments or runs that we want to do for a particular duration, right? So and that's how you call it with a with statement. And one additional optional parameter that can go with the start run method is the name of your run. So you can uniquely define how many ever runs you want, and you can also give them tags as well to have a distinction later on, right? So to simulate the EDA process, we are actually trying to build histograms for each of these features. So there are 10 features, and when we execute this code, you should see 10 plots being generated. But the whole idea around generating this plot was to save it as a PNG and also log it using the log artifacts method. So what log artifacts is actually doing is basically it takes in an argument that is the path for the folder, right? And any number of files and objects that are present in the folder, it tries to log them to the particular run that we are running. So later on, when we want to go back and see what all output was generated or what all artifacts were logged through this run, we can just go to the tracking UI, which I'm going to cover in a bit, and then visualize it from there. So, right. Next up is a few of the hyperparameters that we're trying to predefine. So we have the penalty defined as L2 and the alpha and L1 ratios for the SGD regressor. So this code is pretty straightforward. It's very similar to how we generally try and build our experiments normally. And then we also use the predict method on the regressor that we built that basically runs the predictions from these models. So next up is finding the evaluation, as in finding out how well our model was performed. And for that, we're basically using two metrics like we discussed, RMSE and R squared values. So next up are two more methods that we're using, the log params and log metrics. Both of these take in the key value pairs as the arguments, and the key being the string with which we want to store that particular parameter, and the value being the value for that parameter or the metric that has been either given as an input to the model or coming out in case of metrics, right? So we're storing three parameters that we're trying to put into the model: the alpha, penalty, and L1 ratio, and the prediction, the scores or the final metrics that have been generated, the RMSE value and R squared, are also being logged with the log metric method. One thing we have to notice here is the difference of methods for storing in the parameters and metrics. So metrics solely takes in a key and a value, which is a number, but log params can take key and value, but the value can sometimes be string, like in case of L1 ratio, where the value is L2. Next up is about logging a model. So we did listen a lot of times about flavor, which is a pretty important aspect when we want to try and serve out this model, right? So here within the MLflow module, we're using the sklearn flavor to log a module. And here we give the object for the module that we build. And we also pass in the name that we want to refer it in the for later purposes. So if I run this now, it will probably take a minute. And it did produce a chart here for us to visualize. What I wanted to show you is a terminal window. So that, Karishma, you see the terminal window, right?
No, Kalyan, not yet.
Okay, I think I have to. Okay. You see it now?
Yeah.
Okay, apologies for the mess up there. So yeah, all I wanted to show here was how the MLflow UI, the tracking UI can be initiated. So all you have to do is make sure that you're in the same directory as in where your ML runs are tracked. So what happens when you execute this snippet of code with this MLflow start run command is basically create a new directory called ML runs, where you'll have all the runs that you have executed as of, so far, right? So what we want to do here is within the MLflow demo folder, we want to go to that folder and type in MLflow UI. So it's just as easy as that to trigger the UI. And then by default, we will have a server running in our local host with port 5000. So I'll quickly open that. Right. So this is how the MLflow tracking UI looks. We have an experiment ID, but because we didn't specifically put anything in our run command, we have it as a default 0 value. But what's interesting here is if you scroll down, you'll see all the runs that we have executed on this particular piece of code, and the one that we did a little while ago was the one which says that it was started 1 minute ago. So like I said, you can uniquely distinguish any of the runs with the run name. And I have given it as first run. Then you have a user, which is basically the username from which the user has logged into the machine. Then we also have the source of the code that we're running. So since I'm running a piece of code from my local machine, it does refer to the path from my local machine. And in case you're running any of the code from a Git, it'll also try to store the version of the code for later purposes. So because we use the log model method in our earlier execution of piece of code, we also have the models that were generated, highlighting the flavor with which they were actually stored, right? Then if you scroll further, the metrics that we initially defined, the R squared and RMSE, for each of these runs, we can easily visualize. And we can also see what were the alpha and L1 and the penalties that were used for all these runs. The other cool feature that I wanted to show is basically you can also query or filter these runs that we have, and which goes with a format like this. So we want to have so we want to have a view of all the runs which had an RMSE score of less than, let's say, 63 into a search. So that would basically filter out all the runs that we have, right? And the other cool feature is the ability to download all the data that we have into a CSV for whatever applications that we want to use later on, right? So that is that. And so to go deeper into what each of these runs what each of these runs have as an information stored, you can click on any of their IDs and it'll take to a new page that will look like this, right? So we have the date, when it was run, and we have the duration for which the amount of time that it took to run or execute the code. Then we have the parameters and the values with which we have executed the run. Then we have the metrics and the exact values for those metrics here. So the other part that I was actually referring to originally that the tracking module lets us do is the ability to log artifacts, right? So this is an example. The same plot that we tried to visualize in the notebook is also stored for later purposes. Then because we logged a model with a name called SGD model, that was the last line in the code, we have a folder with the same name here. And that basically can be used with the MLflow model APIs to serve it further. So we did discuss that it contains few files, the ML model file, which basically contains the flavors with which the flavors for the model. It both has a Python function and a scikit-learn function. And the way it was stored, that means a pickle file. And then the exact run ID, which this particular model is actually coming out from. Then we have a conda and YAML file and a requirements.txt file that basically lists all the packages with their exact versions that we want to use. And then we also have the exact pickle file for the model that we want to use. So next thing that I wanted to cover is about MLflow models. So basically what we'll try to do now is basically spin up a new server in our local machine, let's say with a port 5060. And what it basically takes in is, so these are the commands that they originally take in. What would change is the exact run that you want to specify and serve, right? So if you check, so this run is actually coming from the information in the models file. So if I say this is the run ID, and I'm just trying to put the same run ID here and saying that serve me this model at this port 5060. So again, I already have a code running for it because it's a little time-consuming process. It tries to again rebuild the conda environment and then spin up the server. So what we did here is again navigate to the same folder where we have our ML runs directory, and then we are running our command called MLflow serve with the run ID and the port that we want to serve it from. Then the way to call out that model and execute or get predictions for is basically have the IP address, which is our local host, specify the port number, and add a word called invocations. That means it'll try to invoke that model. And the way to pass in the input data is one of the ways is through the JSON format, right? So the first part of the JSON object would be the feature names that we want to pass, and then the exact data, the values of each of these features that we want to predict. So again, spinning up another terminal window, and I'm just trying to pass in the same commands that we have earlier. And then once I do enter, it'll just return me the prediction value for that. So a simple way to just see how ML models can serve models in a platform agnostic way. Next thing I wanted to show is about ML projects.
Hi.
So what we're trying to do.
Sorry, just for a moment.
Sure.
I'm worried that we might run out of time for questions if we continue down. If we
Sure.
keep on going. So
just 5 minutes. I'll try to wrap it up quickly.
All right.
Thanks. So yeah, ML projects would basically contain another YAML file, which basically contains this sort of informations. And MLflow with MLflow, you can actually say run and give the project URI. So project URI would be the exact URL for that Git repo containing a script and the params that we want to pass in. And simply executing it, we need not build and try to manage what all packages it is using or what all environments and so on stuff, right? So the ML project file would automatically take care of what all executions need to be done, and it'll automatically return the result for us. Yeah, we have it here. Okay. Keeping the amount of time we have left in mind, I'll just quickly move on to the conclusions bit. So, so MLOps is a relatively new field, and what it tries to do is basically try to narrow the gap between ML development and ML deployment. And MLflow is one of those tools that tries to address this challenge or this problem in an open source manner. And the three main components with which it tries to do are the MLflow tracking, MLflow models, and MLflow projects. So tracking, again, used to track our experiments and runs, models to serve our model in a platform agnostic way by not keeping in mind where we want to serve and what operating system or what is the architecture that would we want to serve the model in. Lastly, the projects. So if you want to share my project to someone in my team, I can make use of ML projects and wrap my project around that to make sure that whatever results that I produced can be reproduced by my colleague, and he can reuse the same code exactly as I developed it. Lastly, highlighting a few of the resources that we thought are very interesting, and we've also used them to learn and understand more about MLOps in general. The first one being from NeurIPS, where it tries to highlight or specifically mention that the challenges with ML development are much more than just the model development, meaning a lot of things to take care and worry about when you want to take the model from experiments to production. Next up, an interesting survey that basically highlights all the challenges that one would face in the entire development of machine learning lifecycle, right from sourcing the data to putting it in deployment. Then a couple of sources from the MLflow website, mlflow.org, and Databricks, trying to further give some more documentation, examples, and make us understand what is MLflow and what exactly it can be used for. The Databricks ebook also contains some information about managed MLflow, that is like a layer on top of this open source framework that is a feature in the Databricks platform itself. And lastly, if you want to get started and hands-on experience with MLOps, we highly recommend this book called Beginning MLOps with MLflow, which basically gives you examples and use cases to let you play around with deploying models in all the cloud platforms. Yeah, that's all we had. We'll be happy to take up any questions if there are any.
So thank you so much. That was great. MLflow looks like a fascinating tool. So we've got something from Kim. So it's more of a statement than a question. As a DevOps engineer, it warms the cockles of my heart to see that some excellent thought is going into this area. So that's great. Thank you, Kim. Here is an actual question from Chris Steenkamp. Can you log the version of the data sets that was used to train the model?
Yes, we can. So yeah, you can use the same artifact method like the way you used it for the images to log, right? So later on from the raw data, let's say you apply any transformations or imputations, and after which you want to store a copy of that, you can use the log artifacts method for that.
Okay, that's great. Let's see. So this is a related question that I snuck in. If there is an error, then does MLflow have some nice way for you to access the traceback through the user interface?
I think you'll have to try catch them yourself.
Okay, so some supporting process will have to run it. Okay.
Yeah. In some cases, it might be helpful to look at the UI for the stages, and you can go back and you might be able to identify where it's failed from your original code source. But the UI does give you an overview whether it's failed or whether it was executed properly or not, or it was just terminated.
Okay, awesome. Then I have another question. So how do you handle scheduling and data preparation and pipelining? So I once implemented MLflow plus Airflow, and it seemed like a good combination. I'm curious about the supporting tools, the infrastructure that you use to support and feed MLflow.
So I think MLflow is very much compatible with Airflow, and both of them were developed by Databricks. They are both running on some really good infrastructure, and the optimum choice is of course Airflow. Apart from that, you can also try scheduling with Databricks Community Service, other than the local tools that we have, for example, crontab or Windows Scheduler in some scenarios. But yeah, the new combinations that you could try would be the Databricks Community Edition. It is free. You can run, you can create your notebooks there. You can use MLflow there from the tracking, and there are a lot more features available within this Community Edition, which is very helpful. And it is not at all charged. The moment you use it, you can turn off the resources that you use to run your notebook, and your data would still be stored in the environment that you're using, and that doesn't go anywhere in case you're using from Databricks file system. And furthermore, the job scheduler is really helpful. It would also give you emails, triggers that help you identify, okay, my job failed, and it tried to trigger it, but it failed, and where it failed, you'll be able to go back and trace those steps when you click on the job, and it outlines the entire notebook for you and the step where you can debug your notebook.
Okay, that's awesome. There's another question here. Question from Carl. How do you avoid these histories from filling up with wrong results when you're iterating on a solution? Okay.
You can always go back and delete any of the individual runs that you think are irrelevant. That's one way, although it's a very manual and time-taking process.
Okay. You could also
or the download CSV option that you could further visualize and analyze further to see or narrow down or filter out those ones that you think are irrelevant.
Another feature that I particularly like in the UI is you can group the runs together. For example, on one project, you are calling it a regression model. You're working on different runs. You're trying 1,000 different models on it, 1,000 different combinations of the data on it. You can track them and club all the runs into an experiment, which is also available in the UI, and that's how you can group everything together. And within each experiment, yeah, when you want to retrieve the useful results, you can keep them, and the rest, as Kalyan mentioned, can be deleted. But yeah, it actually helps you keep a consolidated file of everything on a local server, and that data doesn't go anywhere. You have that always handy, and a very useful way to visualize through the UI, I believe.
Okay, awesome. I have another question that I snuck in. So Sheena asks, let's say you have a web app built with something like Django or similar. If you want to train your model using MLflow, then what's the best way to get the data you need? So there's a couple of options. You could query the database directly and get some data, or maybe you prefer to have some APIs that are custom built for this purpose, or you want some kind of export of the data to a completely different system. So how would you deal with like a Python web framework that has the data, and now you want to feed the data to MLflow? What would your preference be?
So in this case, you could use a Python function to predict, and at the same time, whatever data you are in, whatever queries you are directly feeding from the web app, you could always log them before you even begin with your prediction, right? That will help you go back and see how your model is doing overall, and see if it has degraded over time. Do you want to retweak it a bit, or maybe build something new on top of it? But the best way is using Models API that helps you deploy this as a Python function onto a web app which is built either in Django or Flask or any other available tools.
Right. So you don't have much of a preference about how you fetch the data in the first place?
No, that depends on developer to developer, I would say.
Okay. All right. Cool. All right. There's one more comment from Kim van Beek. It's hard enough to properly maintain just one or two deployment tools! ! Those are some knowing smiles. Yeah, so I think we are out.
We wanted to introduce this to everyone. We believe that the open source community, like developers who are still learning or doing any of their own models would be really helpful, because we both have gone through this trouble ourselves when we want to reproduce each other's work, or we want to just reproduce our own work from, let's say, weeks ago. So this is really helpful in all of this.
Okay, that's awesome. We are out of time. Thank you so much. That was a fantastic talk and very insightful. I'm sure a lot of people will find it useful. And that's the end of the broadcast. Cheers, audience.